Breaking news, the extreme and now deadly weather this holiday weekend. Flash flooding and record rain in the south, nearly 10 inches drenching San Antonio in just 8 hours.
Over the weekend, more than 100 tornadoes swept through Oklahoma and Kansas. The National Weather Service called it a month's worth. Behind the system, snow and near freezing temperatures in Minnesota. Farmers have watched it all nervously.
To say that they're concerned would be an understatement.
The extremes follow the hottest March ever, with more than 15,000 records shattered.
This is something I've never seen covering traffic above Metro Atlanta. Some drivers stranded in their cars for more than 20 hours.
It rained overnight in Los Angeles, about 1/10 of an inch, and these days, even a few drops is enough to make news. But it's not nearly enough to make a dent in one of the worst droughts in history.
Drought in Mexico, the worst that some parts of the country have seen for 70 years. Here in the state of Chihuahua, one of the hardest hit, 80% of crops dependent on rain have been lost.
First of all, greenhouse gases are something that we've understood for 100 years. This is not anything new. There's no debate about, how greenhouse gases work or anything like that.
So in just a very short amount of time, we know that humans have fundamentally changed the composition of the atmosphere.
We know that if we put a lot of heat-trapping gases in the atmosphere, it's got to change the weather. We've put so much into the air, about a 40% increase in CO2 since the 1800s. That has to significantly change weather patterns.
All global climate change affects different parts of the globe differently. But in the Arctic, it occurs as warming, and the Arctic warms twice as fast as the rest of the globe.
But the Arctic is feeling the effects of global warming first and strongest. And the reason for that is snow. When you raise the temperatures, you decrease the amount of time that there's snow on the ground. Snow is very reflective, but if you remove the snow, the surface is very absorbing. And so you get a strong warming signal.
Implications. So our projection of the overall warming of the Arctic, again, if we do nothing about it, is that a 95% range will be between 6 and 16 degrees centigrade warming, with the best estimate being 10 degrees centigrade warming. And that's why there was 70% chance of being greater than 8 degrees. But it's quite possible to be significantly above 10 degrees centigrade, at which case, it will just be how fast will Greenland totally lose its ice sheet and other very risky outcomes.
The Arctic is important. The Arctic is heating up more than twice as fast as the rest of the globe, and because we're heating up such a big part of the world, more than we're heating up the rest of the world, that means we're changing the difference in temperature from the pole to the equator. And that has significant impacts on weather, because the winds blow in response to changes in pressure and temperature. If there's not as much pressure to try and equalize, the winds aren't going to blow as strongly. They don't have to move as much air around. So that when you change the Arctic by heating it in this way, you're going to change global wind patterns. And those global wind patterns are critical for deciding where rain-bearing low-pressure systems go and all kinds of weather effects all over the world.
Because the Arctic is warming so rapidly relative to the lower latitudes, that this is going to have a fundamental effect on the jet stream. And the jet stream is what controls our weather down here. So anything that affects the jet stream is going to have an impact on people personally and in places where a lot of people live.
You've got a system that's very near the point of freezing, and just small shifts in it can cause a cascade effect to make bigger shifts. So what happens as we uncover more and more ocean up there, we're significantly impacting the climate in the Arctic. We're warming it up, and that has an influence on jet stream patterns. In particular, we think it slows down the jet stream, which means now that we have more of these kind of long loops in it, And since the jet stream acts as the boundary between cold air to the north and warm air to the south, now you're seeing a situation where you get one of these big bends where you get a lot of warm air funneling up very far to the north where you don't often see it. And on the reverse side, you get a lot of cold air coming far to the south on the other end of that jet stream loop. We call them troughs and ridges. So we're seeing a lot of situations where we get these sort of extreme weather situations, warm on one side, cold on the other, and it's causing a lot of flooding problems, heat wave problems, and cold wave problems as well.
Temperature difference between high latitudes and low latitudes. And we know that the Arctic is warming faster than the rest of the globe, so that reduces that north-south temperature gradient, and it should weaken the westerly winds that bring our weather systems. So that's one change that we should expect. And we also know that generally when we have a weakened westerly wind flow, that you tend to get a more variable circulation. The Rossby waves, or the waves in the flow that produce our weather, become more amplified and become more extreme. And so we suspect that between those two effects, the more amplified circulation pattern and a slower moving weather pattern, that the extreme weather that we get now and in the future will intensify and become slower moving, and therefore the impacts could be greater. Well, yeah, that blocking gets into the realm of weather and climate. So when we have blocking, it means that the westerly flow of these atmospheric waves basically comes to a halt in a region. And so it literally blocks the flow, blocks the pattern. And when we get those, that's when we get these long duration extreme events, like long heat waves in the summer, or droughts, long cold waves if you're on the wrong side of the wave.
What you're basically doing is decreasing the temperature gradient between the equator and the pole, because you're warming the poles much faster than the equatorial region. That changes weather regimes. Weather regimes feed on the north-south temperature gradient, the ones that we're sort of familiar with all the waves in them. So there's a lot of research going on with general circulation models to try to see the implications, but there's little doubt there is not total agreement exactly what will happen, but there's little doubt that you'll have changed the energetics of the entire northern hemisphere if you allow the Arctic to warm up very substantially.
Our hypothesis is that extreme weather in general would become more common, more intense, longer-lived, without differentiating at present between cold waves and heat waves and droughts and so on. But I'm presenting some research at this conference where we're targeting a signal, a prediction in climate models of hotter and drier conditions over continents like the United States. And so our target region in this part of our research is it's more or less the Central Plains, and becoming hotter and becoming drier. And what we're seeing is that our interpretation is that much of the circulation changes in the atmosphere that's producing those hotter and drier conditions are stemming from the Arctic. And it appears that it's because there's a reduction in snow cover over the Arctic, which then means an earlier warm-up in the spring, which means the moisture in the soils becomes depleted, and it's sort of a positive feedback. And so the hotter and drier the soils become, the warmer and drier the atmosphere becomes, and the circulation pattern becomes more favorable for reinforcing that extreme weather. So the Arctic, in that sense, helps to produce this change toward warmer and hotter drier conditions, and then the slower speed of the weather systems help it to persist.
Permafrost carbon feedback is an amplification of surface warming due to the release of large amounts of carbon dioxide and methane from thawing permafrost. There's roughly 1,700 gigatons of organic or carbon in the form of frozen organic matter in the permafrost. As we burn fossil fuels and temperatures increase, that begins to thaw out. And once it thaws out, it'll begin to decay and release carbon dioxide and methane to the atmosphere. And this will amplify the warming due to the burning of fossil fuels.
When we talk the terrestrial permafrost, the production of methane occurs, as you was absolutely correctly, when the grounds thaw, so the permafrost melts and this organic matter becomes available. And this is where the production of methanogenesis starts.
only in the little patch of Siberia there is more carbon, organic carbon stored than in all world above ground biomass. So all the trees you would see now outside in the tropics, all the grasses, all the trees around San Francisco, this redwood, all the tundras, everything, you cut down everything, put it on one balance, and you put all the carbon which is in a little part of Siberia, Yakutia, maybe 1 million square kilometer, and this amount of carbon will be more.
You know, the organic matter we're talking about is essentially, you know, dead grass roots and things like that, and that becomes frozen in the permafrost. And once frozen, it remains stable. It's just like broccoli in your freezer. If you keep the broccoli in the freezer, it'll stay okay. It'll stay stable. But if you take that out and put it in your refrigerator, it eventually thaws out and it'll go bad. So with the permafrost carbon, essentially, as long as the organic matter stays frozen, it'll stay stable and in the permafrost. But if you thaw that out, it'll begin decaying. Once it starts to decay, it'll release carbon dioxide and methane to the atmosphere. And that, of course, will contribute a little bit more to the warming, which will promote more thawing, and so it becomes self-sustaining. So it's a true climatic tipping point.
There's more and more attention to this permafrost carbon feedback, which is based on all the carbon it is stored, mostly, at least we know. We know how much it is on land. And we're now trying to make estimates of how much that could be by, for example, 2100. And they estimate that that's going to be, there's now about 800 parts per million CO2 in the atmosphere, and the estimates are that that could be increased by between 50 or 250 ppm, roughly. I mean, that's quite a lot if you compare it to the number now.
There is some release. The thawing of the permafrost has already begun. We already see increases in the thaw depth and warming of the permafrost itself. And there has been some release of old carbon from the thawing permafrost. However, what we expect to see is a kind of tipping point where the Arctic regions, the thawing of the permafrost becomes so great that a large amount of organic matter thaws out and you get a release into the atmosphere. We expect this tipping point, which is essentially when the Arctic changes from absorbing carbon dioxide from the atmosphere to releasing carbon dioxide to the atmosphere. And we expect this to occur within 20 or 30 years. We expect the permafrost to release roughly 120 gigatons of carbon into the atmosphere by 2100.
And of course, releasing all of these greenhouse gases from all of the stored organic matter in the Arctic region is another amplifier in the system. So that's what is the big risk, is that you're just activating more and more amplifiers that'll take the human-driven part of it and accelerate it. So it's a big risk, and we ought to be doing things that will lower the risk, and pretty much that means we need to stabilize the level of greenhouse gases at levels that are not too much greater than those we have today.
I think most people that study the thaw of permafrost, which is definitely happening, we just don't know exactly how quickly and to what extent it will all turn into greenhouse gases. But most people measure things on land.
The methane is always produced in the sediment below any kind of the water body. Would it be the fresh water or the seawater? This is where the methane is produced. It produces in a sediment. Why in a sediment? Because there is anaerobic conditions where there is no oxygen. So when you have this sediment layer of thickness sometimes it needs just a few tenths of centimeters, sometimes 1 meter. And everything that is thicker than 1 meter of sediment produces a methane. And the amount of this methane will depend on how much organic matter available for microbes, bioavailable for microbes in this very top sediment layer. And the thicker the sediments, the more potential for this methane to be produced, because the thickness means that the volume increases. And what is important even more, that when the sediment deepens more than 150 or 200 meters, there are, besides that, the microbes produce methane, plus the temperature increasing, and this allows microbes to produce methane more efficiently. And plus, if it goes even below, there's a thermogenic processes which are step in and produce additional methane. So this means that if you have the sedimentary drape of few hundred meters or few kilometers, it is what we have in East Siberian Arctic shelf, and what differs this shelf from all other areas in the world ocean and the continental shelf, that the sedimentary drape in this particular shelf area is up to 20 kilometers. And all this huge, massive amount of sediment is producing methane. It produces constantly. And it produces wherever the sediments accumulate all over the world ocean. But what is the difference? The difference is that in the world ocean, wherever methane is produced, it is lighter than air, and it is ascends. It's just floating up, and it reaches the surface of the seafloor, and it releases to the water. And because the water is deep, there is specific kind of microbes live in this water, which use this methane for their metabolism. They oxidize methane, extracting the energy for their living cycle. And this is it. So this methane never reaches the atmosphere. It stays, it dies in the water column and never reaches the atmosphere. So this means that despite that the methane is produced all over the world ocean and any particular environment in the world ocean, the amount of methane actually releasing to the atmosphere is very little. But when you go to the East Siberian Arctic shelf, first, because the sedimentary drape is very thick, the mean depth of sediments in the world ocean is 1 kilometer. The depth of sedimentary drape in the East Siberian Arctic shelf is 20 kilometers. The area is huge, it's 2 million square kilometers. It's the largest shelf in the world ocean. And it is the shallowest at the same time. This means that any methane released into the water column, especially if it is bubble induced and bubble transported, has a chance to be released to the atmosphere. And even more important, this in the world ocean, when methane is produced, and as I said, it releases to the water column, it releases constantly because there is no caps, there is no seals, there is no captures, there is no accumulation of methane, with a rare exception of specific areas. In the East Siberian Arctic shelf, despite that the methane has been produced for hundreds and thousands of years, it has no chances to be released because the permafrost, which is frozen ground, is seemed to be serving as a cap. It captures the permafrost. It seals it beneath the permafrost. And this is what causes the huge accumulation of preformed. I mean that the preformed, the methane has been produced before it is given the chance to be released. It's a big difference. In the East Siberian Arctic shelf, it could be that what is released in insignificantly more than what could be produced, because not only the methanogenesis kind of turns on, but release of methane from beneath the permafrost, from the seabed deposits, which could be the free gas, which could be the hydrates destabilized. This could be huge amount of methane, which only needs to be provided with the gas migration paths, so the way to go. And this could be the column within the permafrost, which we call talix or chimney or any kind of thawed-through thawed areas. Or this could require the entire permafrost to be discontinued. So to come up with the idea what is the state of the permafrost, we drilled the permafrost from the fast ice during the winter time. So we brought the drilling rig and just drill. That was a dry drilling. When your auger goes through the sea ice, which is about 2 meters thick, through the water column, and all the way down to the sediments. We extracted this sediment core from this borehole. We investigated, we measured temperatures, we investigated the granulometry properties, and so on, to show that, and we finally show this and reported in this particular paper, that the thermal state of subsea permafrost, despite that it is just few miles apart of its countertop, it's the terrestrial permafrost, the thermal state of subsea permafrost is at least 5-10 degrees warmer. So this means that the subsea permafrost, to approach the thaw point, it's less time required. We're almost there, almost reaching the thaw point. We strongly believe, that methane emissions from the East Siberian Arctic shelf affect not only the Arctic area, Arctic region alone. The methane emissions from the East Siberian Arctic shelf do affect the globe, and they will affect the globe even more upon further permafrost degradation. As this greenhouse gas has been building up, carbon dioxide has been building up in the atmosphere, we've had a gradual warming, that's what's called global warming. This has over time thinned the ice that's floating on the Arctic Ocean. So it's just generally warmer everywhere, so less ice is growing in the wintertime up in the Arctic. So as the ice has gotten thinner and thinner and thinner, it's become more vulnerable to any changes in wind patterns, changes in the amount of, say, heat that's been blown up by the winds up into the Arctic, any kind of just weather-related events like this. And so what we've seen happening over time is that the ice has become more fragile, basically. And so more and more of the thickest ice has either melted or it's just been transported right out of the Arctic Ocean into the North Atlantic, where it eventually melts. So we're left with an ice cover that's not only half as big as it used to be, but it's much, much thinner than it used to be. So if you think of the volume of the ice that's left, so that's the area times the thickness, we've actually lost about 3/4 of it just in 30 years.
The Arctic could warm somewhere between 6 and 16 degrees centigrade by the year 2100 and continue to warm after that, of course. For sure, by then you'll have activated the release of some of the methane and carbon dioxide, and of course we would lose all of the summer sea ice. That is already occurring, and that's another amplifier in the Arctic climate system.
When you melt Arctic sea ice, you uncover dark ocean, which absorbs a lot more sunlight and heats things up, which melts more ice and causes this kind of vicious cycle where the Arctic heats up more and more and more. This is one of the reasons why the Arctic is heating up so much more quickly than the rest of the globe. You've got a system that's very near the point of freezing, and just small shifts in it can cause a cascade effect to make bigger shifts. So what happens as we uncover more and more ocean up there, we're significantly impacting the climate in the Arctic.
As time goes on and it gets warmer and warmer and warmer, the capability of the Arctic to exchange cold air with warm air from the lower latitudes, of course, becomes less and less effective as a cooling mechanism for the middle latitudes.
Yeah, the Arctic is kind of like the canary in the coal mine. Do you say this in English? So it's the first thing that actually gives an alarming signal to the rest of the planet.
Now, the reason we haven't seen as much action as we should on climate change is there is a very successful, well done, and well funded contrarian campaign to discredit science, to highlight uncertainties, to delay action. And the companies doing this are, of course, the oil companies and the coal companies. Rich industries in the past, whenever they've been threatened due to scientific findings that say their product is dangerous, will launch PR campaigns to try and minimize the danger, delay action, and so on. We saw this with the tobacco companies, the asbestos industry, the chlorofluorocarbon industry when the ozone hole was found. And some of these same PR firms and some of these same scientists that were involved in those campaigns are now working on behalf of the oil companies to delay action. And they've been very successful. They're very good at it.
Anything we can do to slow down carbon dioxide emissions is going to help some. As I said in the beginning, though, we've already put so much carbon dioxide in the atmosphere, and that carbon dioxide lives a long time in the atmosphere. So even if we could stop completely now, we're still looking at a lot more change coming our way. So, but I still, that's kind of a gloomy, a gloomy outlook. But that said, anything we can do to slow down additional emissions is worth doing.
The only way to really prevent the permafrost carbon feedback from starting is to reduce fossil fuel emissions. And I think that is the key. Your viewers, if they walk away with the idea we must reduce fossil fuel emissions, and just so, not to sugarcoat it or anything, but we really have to reduce it by 80 or 90%.
We can't wait for perfect knowledge of what those thresholds are. So one of the things we do, that's why we do many forecasts with different assumptions, to sort of show the spread of the outcomes. And that enables you to say, now if I stabilize it at levels not too much greater than what we have today for greenhouse gases, that you lower the risk, particularly of very large amounts of warming in the Arctic region. And it's dramatic to see what the lowering of the risk is. And we need to start that now. We can't wait until the researchers say, we've finally pinned down exactly what the threshold is. I think by the time that happens, with great accuracy, again, we will have been building up the greenhouse gases to higher and higher levels in the meantime. So I think we've got to go on both fronts. We need to move to mitigation by lowering greenhouse gas emissions, and we need to continue the research to understand more and more at what levels of warming do you get these dangerous outcomes for not just for the local regions, but for the planet as a whole.
The dawn